Hey there, class. We're going to look at solving a two-dimensional kinematics problem, sometimes known as a projectile problem. So let's take a look at it. This is a continuation of a previous problem that we've looked at before. And there's just one little detail that's a little bit different here. And that is the fact that the platform is 10 meters above the ground. So let's continue and take a look at what's going on here. So basically, we have this platform right here that the ball's on. As it is struck from the platform, the ball is going to travel along a parabolic path. A parabolic path is going to make this ball land somewhere over here. So the velocity initially is going to look like this. And again, this is, if I'm not mistaken, this looks like 33 meters per second. And it's at an angle of 40 degrees above the horizon. Now, as this ball travels through the air, it is going to travel again along a parabolic path that's going to look something a little bit like this. Now, as it gets to the ground, this is one of the red flags that I want you to look out for here. The red flag that I often see students make is they assume that velocity is equal to 0. Now, I want to be very clear on this. Velocity is not equal to 0 at the very end here. Okay, we are talking about a free fall situation. The ground has not actually started acting on this. So you want to be very careful that you don't make this mistake that a lot of students do make. So here we are. The velocity will actually, in fact, look something kind of like this. It's going to be in some kind of downwards direction where it's going to be directed in some angle below the horizon. And I guess they don't need to know anything about that in this problem, but at least we can show that we understand what's going on here. As the ball travels through the air, it is going to have an acceleration. That acceleration, of course, is what we know as gravity. And we know that it's 10 meters above the ground. So it's going to start at this location and it's going to travel down to this location. That's how far it travels, or I should say this, that's our vertical displacement that the ball is going to undergo. And that is a 10-meter vertical displacement. We also know the ball is going to start here and end up going over here to there. That's our that's a horizontal displacement. And this is actually what we want to find in part B. So this is the part B find. All right. And what we also want to know is it's going to take a certain amount of time to travel over here. This is going to be our find for part A. Whoops, I just said B. How about I correct that and say A? So that's part A. All right. So let's start putting in what we want to do here. Now, when we separate our knowns, we always want to separate them out into X direction and Y direction things. We don't let these things cross over because our equations only work for one-dimensional problems. So in effect, a two-dimensional problem is really two one-dimensional problems put together. And of course, there is a tie-over, and we've talked about this in another video, but the tie-over between this is the non-vector, the scalar here, and that is the time that connects the two together. But let's kind of list out what we want to find here. We want to find this, and actually we want to find this. So that means we can find it from either the X direction information or we can find it in the Y direction. All right. Initially, my velocity, and this is another red flag, I see a lot of students that want to write something like this. And this, again, would be a red flag. We, of course, should know this because if we look at our initial velocity here, we'll notice that our initial velocity is at an angle. And so that's neither in the X direction nor is it in the Y direction. So we would actually have to calculate the components of this, this vector. So I'm going to do that real quick here. And we're going to draw that over here on this other side. This is just what I'm going to call my helper triangle. And I'm just going to do a real quick rough estimate here of what's going on. This angle right here is the 40 degrees. This would be my x component. So we'll call that, how about, let's call that, since it's the initial velocity, we'll call that VOX. And we'll call this the original velocity in the y direction. Now, in previous videos, I've talked about how to find components, so I'm not going to spend a lot of time here discussing it. But this velocity here is the 33, and again, we're really talking about magnitudes here, so let's not worry about the vector symbol. This is the 33 meters per second. The x component is going to be 33, and that's going to be the cosine of 40 degrees. And again, if you need a little bit of help on how to do that, check out my previous video on this. And this is going to be 33 sine of 40 degrees to find this one. Okay, so going back down to show we understand here, when we go into the knowns, I want you to be careful here that you don't make this red flag mistake that a lot of students want to make. Now, when we actually do calculate that out, you will find that the original velocity in the x direction, let me just look that up here, looks like it's going to be 25.3 meters per second. All right. In addition, because there is no forces acting on this ball in the x direction, there's zero acceleration in the x direction. That is kind of a conceptual understanding you just kind of need to know about projectile motion. So what that means is that the final velocity in the x direction will also be the 25.3 meters per second as well. When you go over to the y direction and we start listing our knowns out here, we'll know that this was 10 meters. The initial velocity, again, if you go up here and you do the calculation for 33 sine of 40, you will find that the original velocity is 21.2 meters per second. We don't actually know this at this point. We don't know how fast it's going at the end. But we do know the acceleration. We know that, of course, the acceleration is gravity, which is 9.8 meters per second squared. Now, something we haven't done yet, and something I always like to do here in any problem, is we should define some positive directions. I noticed that pretty much all my vectors, or many of my vectors, are going to the right. So I think right words is a good definition for positive in the positive x direction. And I noticed that there's at least two of my vectors here. We have the gravity and we have this displacement going downwards. So again, I like to stick to pretty much keeping as many things positive as possible. I am an optimist by nature after all. So I tend to look at the positive side of things. So as we go through here, to give this a direction, that would be positive. This is also positive. The acceleration in the y direction will be positive. And this was positive, and this was actually a negative value here. Okay, let's take a look at a strategy. Basically, again, we assume constant acceleration. So we know that if I'm assuming constant acceleration, we can use kinematics to do this. So that's going to narrow us down to some equations that we want to take a look at. And as we take a look here, I want to take a look, and what was I trying to find again? Trying to find out how far something is traveled, and I'm trying to find how much time it takes to do that. Okay, so one of the problems in the x direction that we're going to find here to do this is that to find the delta x, there's no way to do this if I don't have time. So that right away leads me to know I'm going to have to start in the y direction when I actually solve this problem. So I'm going to try to look for some equations that actually help me out. So to find time, with given information, what I'm going to do is I'm going to take a look at my equations. And as I do this, I'm going to notice that there's one equation that sticks out to actually solve this. And that's this equation right here. It's my delta y equals the original velocity times time plus 1/2 times the acceleration. And since we're dealing with the y direction here, I'll put a subscript of y times t squared. Okay, and again, I just do my kind of my check off. I have this, I have this, I have this, and this guy right here and this guy right here are what I'm trying to find. So the fact that I basically have the one thing that I want as my unknown and all my other things are known, this is a good thing for me. So as far as the equation goes, I think this is a good candidate. Okay, so I did a little work behind the scenes here. Wanted to just kind of show you a couple things. So when I'm thinking of the quadratic formula, I'm thinking ax squared plus bx plus c equals 0. So I did take my equation that I had come up with and I decided to put it more in that form. I believe, if I'm not mistaken, that's called standard form. And so what actually ends up happening here, the thing inside the parentheses here, notice the orange, these are my a, my b, and my c. So the quadratic formula is down here, and of course the x in this case is actually my t instead of an x. So I've put my substitutions in, and I've actually calculated out, remember there's always two solutions. There's the plus solution and then there's the minus solution. So a couple little details, some things that you really need to be careful of here, is that when you're doing this, the positive and negative direction is very important. And you'll notice here, again, because my initial velocity is actually upwards in the y direction, it actually ends up being negative. So when I do that down here, you'll notice that there's a negative here and that there's a negative here. Now, of course, this one's being squared, so in the end, that's going to be a positive thing. But you do want to make sure that you're being very cautious here. This is definitely something I see a lot of students make mistakes. They forget to account for their positive and negative directions. So let's talk about this here, the positive solution, and then there's a negative solution. And you might say, well, which one? Hopefully it's pretty obvious that the negative solution doesn't make sense in our case, but it actually does physically mean something. And what this is solved for is basically is if the ball were to be hit from back here, it would have happened, I don't remember the number here, about 0.4, we'll say 0.4 seconds. It would have been about 0.4 seconds before. So if the ball was hit from here to get up to this point, it would actually be about 0.4 seconds to do that. So there is some physical understanding of what that actually means, but it really doesn't mean anything for us. So for our purposes, the 4.76 is what we need to do. Okay, so the second portion of this problem, this was part B, I believe, part B. The second portion here asks us to find the delta x and how far it goes. In this case, it's just a magnitude, so I'm not too worried about the direction. But as far as equations go, because I just found time in part A, I can now use that in the equations. So I do have here an equation that I believe will work. It's actually the same exact equation we used before. One thing to note, this acceleration, be very careful here, this is an x direction acceleration. And it just so happens that if you recall from our knowns, if I go up here, notice in the x direction, remember this is the x direction here, it's listed under by x, all these things are x's by the way, it is 0. There is no acceleration in the x direction. So to simplify this, this term is actually going to be, it's going to get canceled out. So in the end, what this is really going to look like is delta x equals the original velocity in the x direction times time. So let's go ahead and substitute and solve. So delta x equals, and I don't recall what the number was, I think it was like 23 something, 25.3, there it is. 25.3, and that was in meters per second, and we're multiplying it by, I think it was 4.76 seconds. And when we do this, what we'll end up with is going to be about 120 meters. So if we take a look back what our questions were asking, if we were responding to our questions, and by the way, that is part A and part B. There were two parts to this problem. The first part asks us to find how much time did it take, and we kind of discussed that already, but the time it takes for this ball to hit the ground is actually going to be 4.76 seconds. In part B, they're asking for how far it goes. That's not a vector, so we don't need the vector symbol here. We don't need to worry about direction. But the magnitude is going to be 120 meters. And so